restart
This meeting is being recorded.
at least one engine and make it into an airport. But it still is a major hazard, obviously. And so in response to those events, it's really starting in 1982. There's an organization called the International Civil Aviation Organization. It's a United Nations treaty organization. And their job is to write the rules for air travel. So if you fly from one place to another, the rules regarding which air traffic control unit is in communication with the plane at different parts of the flight, those are determined by ICAO. There are a million rules, and they decided they had to have some procedures developed for how volcanic eruptions are communicated. And so some of those procedures use existing facilities, but volcano observatories are throughout the world, not everywhere, it turns out. Like there's volcanoes in the Western Pacific that have no volcano observatory anywhere around them. So you won't get a notification if it erupts unless somebody is watching satellite images. But in Italy or many parts of the United States or others, the volcano observatories hopefully will know when an eruption occurs and can communicate that to these other places, meteorological watch offices, which are around the world, like the National Weather Service office in Portland is a Met Watch office. And so they have formal messages. SIGMETs, significant meteorological events, are messages they send out for any kind of meteorological event, but includes ash clouds if they see them. Area control centers, which control airspace. And then the new one that they created, really starting in the 80s, but developed and identified in the 90s, were volcanic ash advisory centers. So these were places set up specifically to detect volcanic ash clouds and forecast where they go. So in the 90s, they divided the world into 9 regions. And within each of those 9 regions, they said, okay, there's going to be one center that tracks ash clouds in that region. So you can see where our center is the VAC region, which includes the conterminous United States, all the way far south is Ecuador, to the Mid-Atlantic Ridge and to the Western Pacific. So that there's a NOAA office near Washington, D.C. It's actually in the building where the NOAA satellite group is, NOAA NESDIS operates. So you go up to one floor, there's several desks with a forecaster at each desk, and they are scanning satellite images and communicating with volcano observatories and issuing notifications if they see them. This is a very busy region because it includes Central and South America, northern South America. So they issue about 600 volcanic ash advisories every year. The North Pacific is, well, you can see that a lot of the North Pacific is overseen by the London VAC. So the UK Meteorological Center in Exeter has a group that has the same responsibility. It turns out the only volcanic region in their volcanic center in their region is Iceland. And so they don't get nearly as many volcanic ash advisories issued, but when an eruption happens, it's a big deal, especially if it goes to Europe. So they're constantly worried about the big event. And so each of these has a center, which almost all are national meteorological agencies. Buenos Aires VAC is the Argentinians, the Tokyo VAC is the Japanese Meteorological Agency, the Wellington VAC is the New Zealand Met Office, and the Darwin VAC is the Bureau of Meteorology in Australia. And so we also in the US have developed protocols for how to communicate between agencies in the event of volcanic eruptions that threaten aviation. And really starting in the 2000s, somebody from our office, Marianne Gaffandi, started collecting accounts of volcanic ash encounters. And in some cases, there's probably actually a lot more encounters than are tallied up here, because there probably are cases where some airplane flies through an ash cloud and they get back to the airport and they say, oh, shoot, there's ash in the pitot tubes. We're not going to tell anybody. But these are the ones that have been reported. And you can see there's quite a bump at Mount St. Helens. Pinatubo had an even higher bump. And so this was compiled in 2010, right before the Ea Fiatlayokut eruption. But it turns out that it looked at that time like, well, maybe the number of encounters with aircraft is diminishing, and maybe this infrastructure we put together in the last 20 years is starting to work. And well, that's what we thought in 2010. And the procedure at that time was, well, I'll tell you that in a minute. But so this eruption really changed the landscape. This is the eruption in Iceland that shut down airspace for a week in Europe. It started on the 15th of April in 2010. And what I'm going to show you here is a series of images. In the upper right are satellite retrievals. The satellite images are infrared satellite that have been reprocessed to detect ash clouds. So you see that purple in the upper part of the right image is an ash cloud, and the color is proportional to the amount of ash in the cloud in tons per square kilometer. And in the lower right is the volcanic ash advisory that was issued by the London VAC at the beginning of this eruption. You can see it's April 15th at 12 o'clock UTC in both cases. And one thing to notice, so the way that the VACs, the Volcanic Ash Advisory Centers, do this is they will have a forecaster who is looking at the satellite images, running a model, and then they're going to draw a polygon on the map saying, this is where we think the cloud is going to be at this time or this time. So usually they're supposed to issue a location of the cloud at the current time, 6 hours, 12 hours, and 18 hours into the future. And there's actually 3 polygons on that lower part. Those are for different flight levels. But another thing you can see is that cloud in the upper image, which is the observed cloud and satellite, covers just this small area north of the British Isles, extending over to Norway. And the polygons extend over a much wider area. Turns out that the London VAC was relying heavily on their models and really not looking at the satellite images as closely as they could have. So as time went on, you can see that the cloud is continuing to drift to the east and eventually the south. The polygon's getting bigger because the eruption is continuing. It's putting more ash into the atmosphere. The model is probably not taking it out as fast as the atmosphere is actually taking it out. And so by the end of the 3rd day, there was a polygon covering most of Europe. And the way that the European governments deal with that is that they will consider that airspace closed if the volcanic ash advisory covers that area. In the US, the FAA doesn't actually close that airspace. The airlines are aware of it. They're supposed to fly around it, but it's not enforced as a no-fly zone. So what happened was, you have this huge area, probably most of which doesn't have ash in it, but it was closed to air traffic. There was 300 airports closed for a 3-day period, 100,000 flights canceled, 10 million passengers stranded, a total of probably about $5 billion in economic loss because people couldn't fly, which made it easily the most expensive volcanic disaster in history. And of course, you had these people sitting at airports looking like, where's the ash cloud? And why aren't we flying? And more pressure was being put on the European regulators to say, like, what's going on? Why don't we get these flights moving? So they're going to the London back and saying, like, why are you identifying this huge airspace? We don't see ash in it. And they're going, well, our model says it's there. And they're going, well, if it's there, there's not a whole lot. And there was never any protocol to, it was either ash or no ash that you were supposed to be outlining. And so they said, well, we're going to have to allow flights through dilute ash. And that opened this whole Pandora's box. Well, what's dilute ash? How much ash is going to hurt an engine? And so the European Union went to the engine manufacturers and said over a weekend, give us a number. Like, what can we fly through? And so they had really never done any engine tests for volcanic ash. They had some experience flying through desert sand conditions. Of course, quartz sand is different from volcanic ash. It melts at a much higher temperature. And there was one set of experiments that was done at Ohio State University in the 1980s in preparation for nuclear war. So they told this guy to see how much of ash and dirt and whatever a jet engine could fly through, assuming that it would be thrown up, I guess, during nuclear explosions. So he just threw hundreds and hundreds of, like hundreds of times this threshold into the engine and found that it would stop working after minutes. But they had basically these two data sets, the desert sand conditions and this one set of experiments, and they differed by about 4 orders of magnitude in the concentration. And they kind of took a number that was kind of in the middle and said, well, 2 milligrams per cubic meter. And so the regulators went back to the London VAC and said, we don't want a polygon on a map. We want model output with contours of ash concentration on it. So at the end of that week, the London VAC, the modelers, had to come up with this new product. So it had these different zones, which you can see the outside of the red zone basically is clear flying, less than 0.2 milligrams per cubic meter. The gray zone is between 2 and 4, I think, and the black zone is more than 4. That's not what that says. Yeah, so let's go by that. But basically, they were required to come up with this, and in some cases, these contours differed by only a factor of 2 and in ash concentration. And the modelers were forced to do it, but they freaked out and they said, we really don't know how much ash is in the air. You can't expect us to produce a model with that kind of accuracy. But it turns out the regulators didn't back down. We said, we want this product. And it turned out that they produced it. It got flights back in the air. Of course, the volcano quieted down at that point too, so that helped. So you can see these 3 frames are the amounts of flights in the air on April 17th during the heart of the crisis, April 19th and April 20th as they were getting back into flying. So they did get flights to resume, but they were left with this problem of the regulators are demanding something that we're not sure we can deliver. And by the way, it's a different rule from everywhere else in the world. And are we going to have pilots try to remember which region they're in and what the rules are in each region? And so that became another big point of contention. But there were several things that contributed to this. One was there had never been an eruption that sent an ash cloud to an area with such a high density of airports. If this had happened over the North Pacific, a cloud that size, you could easily fly around it. But if there's 10 airports right under the cloud, you can't avoid them. The other was the over-reliance on model results. The London VAC was just not looking at the satellite images as closely as they could have. A third one was the regulatory structure in Europe. They were actually closing airspace. And then finally, and this is something that we realized found out the hard way in 1980 at Mount St. Helens, when you have scientists and people who have to respond who have never talked to each other, and the first time they're talking to each other is during a crisis, and they don't understand each other's language, and they don't understand what the implications are of different decisions. You have to have an ongoing relationship between those groups, even when there's no crisis. So, and then finally, the zero tolerance policy for ash was an issue. But after this, it turns out the aviation community said we're going to have a series of meetings where these groups can start talking to each other and understanding what they're talking about. So that was, is there any way that we can improve these procedures going forward? But they still had this big issue that there was one rule now for Europe and another rule for the rest of the world. And so a big issue that this series of meetings, it was called the International Volcanic Ash Task Force, and it met in 4 meetings between 2010 and 2012. And the biggest issue was, do we make this a global rule change, or do we stick with the old rule? But there were many other questions, and since this task force was attended by many different groups. So there was the engine manufacturers, what they called the bodybuilders. So like Airbus and Boeing were there. There was a representative from the International Federation of Airline Pilots Associations. So he got up and said, okay, we pilots are going to be the last people who are going to make the decision. Can we even see a cloud that has 2 milligrams per cubic meter of ash in it? And then, the answer is kind of complicated. Well, it depends on the background, it depends on the lighting conditions, it depends on a lot of things. And other people were saying, well, if we're going to validate this, what are the detection limits? So a lot of the decisions that are made by the VACs are dependent on what they can see in a satellite image or some other remote sensing image. And what are the detection limits of those kinds of instruments? How much ash does it take to see a cloud? And so it turned out that ICAO is a very formal organization. So these people would ask these questions, and they would write down these questions, and they would submit them to this scientific advisory group, which I was a member of. So this is a group that was formed actually a month before this crisis. But it consisted of modeling specialists, remote sensing specialists, people who are specialists in various atmospheric measurement techniques. And so we had been established to advise the VACs on the science of ash cloud detection and forecasting. But it turned out in this group, our job was to answer these questions that were posed to us formally and write reports that answered them. And so there were the scientific concerns that were raised. The biggest one, in my view, since I'm a modeler of ash clouds, was how can we provide more accurate models? If we're going to provide models that forecast ash concentration, we have to know how much ash is coming out of the volcano in real time. And the procedure for doing this traditionally has been, there's a correlation between the height of a volcanic plume and the eruption rate, how many kilograms of ash are coming out per second. And we know that because we've gone to several eruptions. Each blue dot on that plot is an eruption where they've measured the height of a plume, where they've gone out and mapped the deposit, and they know the erupted mass. They know how long it took to get out, so they have an average eruption rate. So I think probably Mount St. Helens is one of the ones just above that yellow box there. But if you plot all of them, you can see there's a clear correlation. The bigger eruptions with higher eruption rates also have higher plumes. And so if you see an eruption and you say, well, the plume height is about 10 kilometers, the eruption rate must be about 2 times 10 to the 6 kilograms per second. But then you look at the dashed lines and go, well, okay, there's an uncertainty of almost an order of magnitude on either side. So if you go back to that map of ash concentration that they're supposed to be issuing, and you look at the 2 milligram per cubic meter line, well, it could be 0.2 or it could be 20 within our error. That's how big the error is. And so expecting to come out with contours that differ by only a factor of 2 is not very meaningful. So there's a whole lot that's changed. There was this was one of those moments, you know, it's like in the science of volcanology, our understanding is like a step function, and every step is an eruption. So Mount St. Helens, Pinatubo, Eyjafjallajökull, the Tonga eruption, and so on. And each time there's an eruption, we have new ways of seeing things. We have new instruments. We have better ability of developing models, et cetera. But one thing that this really prompted was more study. And so the US Air Force talked to the 3 engine manufacturers and NASA and said, we need more engine tests. Turns out that the Air Force had a C-17 aircraft that was, whoops, that's not supposed to happen. Can I go back? That was about to retire and be sent to the museum, Air Force Museum in Dayton. And they agreed to put it on the runway at Edwards Air Force Base. And General Electric built an injection system that would inject ash at a known rate into one of the engines. Rolls-Royce said, we'll collect ash. The USGS, we actually went to downwind of Crater Lake, and we got literally a ton of ash from a quarry there and had it milled and sent to them. And so anyway, they did 4 hours of testing on one engine. They wrote a long report, but because there were all these groups that all had their proprietary issues, the report never became public. But the short thing is that it more or less confirmed our view that this 2 milligrams per cubic meter plus or minus a factor of 4 is about the right range where you start to get engine damage. And that was also supported by a compilation done by Rory Clarkson, somebody who works at Rolls-Royce. In the lower left plot, you can see a bunch of bubbles on a figure. So the x-axis is the ash concentration. So he had to estimate the concentration of ash for each one of those cases where an airplane flew into an ash cloud. And he also had to estimate how long it was in the ash cloud. And then he also had to make some statement about the amount of damage. So he drew these zones. So the upper right red one is the one you want to stay out of. That's the highest concentration and the highest time in the cloud. But he showed that there is this region where you maybe can fly for a limited period of time, and then outside that region, hopefully you can fly reasonably well. So, but these are things that we've just learned in the last 10 years. We've also, whoops, I'm going the wrong way, sorry. Developed new algorithms that will automatically detect an ash cloud from satellite images. So what you see in the left, all those purple dots are dots that are automatic, where this algorithm is automatically saying, we think there's ash at this pixel based on spectral properties of the cloud. And it's drawing a magenta polygon around that, and it's following that cloud. So this is something that Mike Pavlonis, who works for NOAA, has developed, and you can get onto a subscription page and get an email every time it thinks it detects an ash cloud. There's still a lot of false positives, so it's not one of these things where you know there's an eruption every time you see it. But it's a significant advance, and of course it's getting better with time at detecting the clouds and failing to detect the ones that aren't ash clouds. But another thing that has really changed is there's a whole new generation of satellites out there that can see clouds that are smaller than we could see before. So these are high. So 30 years ago, when Pinatubo erupted, we had a satellite that got about 1 image per hour. Now, from the GOES 16 and 17 satellites, we're getting about 1 image every 10 minutes. And the pixel size is about 1/4 the size of the old one. So this plot here is from a colleague of mine who compiled the cumulative number of volcanic ash advisories issued worldwide since about 2008. So what you can see is the blue and orange and gray lines are the times when different new satellites were launched. So Himawari 8 is a Japanese satellite that sits over the Western Pacific. GOES 16 is the NOAA satellite over North America, and GOES 17, which is actually now GOES 18, is over the Central Pacific. And so each time these satellites were launched, that curve steepens, which means they're seeing more ash clouds and they're issuing more advisories. So presumably the advisories are getting better, and we're able to keep people safer. Another thing that has developed in the last 15 years is mobile radar systems. Iceland bought one after the eruption of Ea, so they can drive this thing to any volcano that's threatening to erupt and get hopefully a much quicker detection of whether ash is actually coming out. It's much better than seismicity, because that tells you the earth is shaking, but it doesn't tell you if anything is coming out of the volcano. In Alaska, we've also started using a worldwide lightning location network. So this is a network that detects and locates ash or lightning strikes anywhere in the world. And so you can write an algorithm that if it detects a cluster of lightning around a volcanic vent in an area with low ambient lighting, like Alaska, you'll get an email message saying there might be something going on here. And finally, infrasound, which is like seismicity, but it's airwaves. There are infrasound networks now in the North Pacific that can detect eruptions. And then finally, on the modeling side, this is the way that, so this is a photo I took in 2009 in Alaska during the Redoubt eruption. I just wanted to show you this to illustrate how these volcanic ash advisories were issued prior to 2010, and in many parts of the world they're still issued this way. So this is a forecaster when there's no eruption going on. She works at the Alaska Aviation Weather Unit. So basically her job is to write weather forecasts when there's no eruptions, which is 90% of the time. But at this time, Redoubt was threatening to erupt. So you can see, just looking at the screens on her desk, the one on the left is a seismogram. So she's pulling up the seismogram from the Alaska Volcano Observatory. The one to the right of that is a webcam image. So there was a webcam located near Redoubt. So this was probably nighttime, so you couldn't really see what was going on. There's also a satellite image. So if there was an eruption, she may have seen something in the satellite image. In the seismogram, she would have been clued in, and she would have probably called the Alaska Volcano Observatory, or they would have called her. And so that would have been the first clue. And then if it looks like there is an eruption, the first thing she would do is run a model and to see where it might be going. And so this was an eruption that occurred on March 23rd, 2009. And then you might actually have a satellite image from about that same time. And in this case, so that's an infrared image. The oranges and the reds are the coldest temperatures, which means the highest clouds. So that it's most likely that orange part is the volcanic cloud, but it doesn't really look like the modeled cloud. It turns out that in the model, that left arm of the wishbone was much lower elevation. So you'd have to look at the satellite image and go, well, is there not a cloud on the left side, or is there a cloud that's low and obscured by meteorological clouds? And so she would have to make a judgment as to where the cloud is and how do I outline the cloud. And then she would issue an advisor, which is again this polygon on the map. So it's basically a combination of human judgment, modeling, and observation that's used. After EA, there was a ton of papers that they actually had a lot of quantitative data. There were flights that skirted around the edge of the cloud and measured ash concentration. And then, of course, we had the satellite images with quantitative data. And so there were attempts to compare modeled and measured and observed. And this plot on the lower right is the x-axis is the observed concentration, the y-axis is the modeled. If it had been perfect, everything would be lying on that diagonal line, but it's pretty much within an order of magnitude of the observed, which actually was surprisingly good for that case. But there was a whole series of validation tests. But since that time, modelers said there are several modeling groups that do this around the world, and they've migrated to sort of a hybrid method where you actually have satellite images and you run a model and you have an algorithm that automatically compares those. And then it starts a new series of models that concentrate on inputs that do the best job of predicting the observations. So this is an example that was given to me by a colleague in Spain, where they have the modeled cloud on the left without any input from the observations. You have the observed cloud on the right, and in the middle you have something that is modeling informed by the observations. But as time goes on, the hope is that combination of observations and modeling will do the best job of accurately predicting. So, okay, how's this going to go on in the future? Well, it turns out the regulators never did back down on this insistence that we come out with modeled output with ash cloud concentration in it. And this is actually going to be a requirement by 2026 that the VACs that have the modeling capability do this for what they call the significant eruptions. So the really big ones. And the modelers come back and go, well, we're not sure we're ready yet. And they'll go, do what you can. We know it's not perfect. Just do what you can. And so this is still the biggest challenge in the ash cloud forecasting community, is how do we develop better models and compare them with observations. But what we've really seen in the last 20 years, we have much better ash cloud detection algorithms, better satellites, which are seeing clouds more clearly and smaller clouds. And so we think that this is probably a trend that will continue probably for the next few decades. I think it still is. If I were to come back 10 years from now and give the same talk, I'm going to probably continue to say that this goal of being, giving you an ash cloud concentration within 15 or 20% is still an aspirational goal, but it's something that we'll be working towards for a long time. So that's Lake Geneva. In April of 2010, the World Meteorological Organization has this spectacular building right on the shore. And I'm sure they took this, like looking out the window of this building, right when the Ea cloud was coming over. But, yep. Mm-hmm.
You're making me think a whole lot. I was city manager in 1980 when Mount St. Helens blew up. And for for a couple days, they said, you can't do anything about it, we don't know what to do, just let it go. And the one day I can recall, I came home from work at 5 o'clock, and my husband's pickup truck was covered with black ash on the bumper and the top. I was not afraid. I just was thrilled, and I collected all of that black ash. The biggest thing that I'm thinking about now is nobody told us what was going on. Nobody told us how to prevent anybody from suffering, and this is all new. But I also thought, I collected all of that black ash and it's upstairs in my bedroom.
Oh my gosh.
I'm gonna have to go get it. But I appreciate what you're saying, because there was no rules or laws to help people if there was a problem at that time.
That was a big issue, and it turned out that of course, the counties that were immediately around the volcano were all, they were attuned to what was going on, but the counties that were downwind weren't. And there were, so that the Washington State Department of Emergency Management had sent teletype messages to the counties downwind on May 18th saying ash is blowing downwind, but there were no phone calls. And many counties didn't start to worry until they literally saw the cloud coming towards them. And
That's true. And this ash didn't seem to land in this area, in the downtown area. It was more on the hillside, Avery Street, where I live.
Oh, interesting.
And it sort of blew onto the hill, which may be about 200 feet more higher than here.
Oh, wow. That's
But
interesting.
drew our attention. We camped and water skied at the Lake Merwin, I think, for years. So I knew about that. I knew about Mount St. Helens, but I had no clue as to what to do when the clouds started coming to Tualatin.
Was that must have been June 12th or something when it came to Tualatin?
About 81, 80 or something, whatever it was.
Yeah, May 18th went east, but June 12th, I think, was when most of the ash came down to Portland. Yeah.
That big of a time difference?
Yeah.
So the May 18th eruption was a 9-hour long eruption, and then the volcano went to sleep for a week, and it woke up on May 25th, then June 12th, then July 22nd, then August 7th, and another one in October, which I think dusted Portland with ash also. So yeah, so each of these eruptions was a few hours long, but there were several of them.
So Larry, I noticed that you were showing that. Oh. You showed that one picture of the air traffic that was live, you know, after the
it looked like France had not allowed any traffic for the next 3 days.
Oh,
I didn't see.
Yeah,
I don't know how hard that would be to.
I didn't.
I've done an awful lot of flying over in that area, and what they'll do is they'll just completely close the airspace at certain times. Every once in a while they decided they're gonna go on a what's it called when you've got a union and you don't want to work?
Oh,
A
yeah,
strike.
yeah,
That's look.
yeah.
Yeah, we have actually gone from England over to Turkey, and we had to go all the way around out in the Atlantic Ocean to go around France.
Oh,
And that's what
gosh.
it looks like.
Yeah, interesting.
Anyway, does anybody else have any questions? Oh, great.
Okay, so Stephen asked some questions on Zoom.
I have a question.
Okay, let's do one of Stephen's first, and then we'll come. Okay. Okay. Stephen asked early in the presentation, why are the jet engines able to restart if they shut down because of ash?
So I only know the speculation, which is that the ash, as it cools, it cracks, and it may just break up as it's cooling and allow some of the engine parts to start moving again. In the cases that I know, like Captain Moody, who was in that 1982 747, he gave this long 1 hour explanation of they were trying constantly to restart the engines over it was 15 minutes, he said, that they were without power, which blows me away. I don't know how they couldn't have stayed in the air that long without power, but they were constantly trying to restart the engines. And yeah, well, I mean, there were people. I don't know how full, but yeah.
I was always surprised in 2010 that Iceland had such an ash cloud, because you don't think of that. I think of Iceland as being very mafic and not very explosive. So do you have an explanation for why it was acting like a stratocone eruption?
This was an interesting one because actually the eruption started in March. It was a flank eruption, and it was a mafic. It was a basaltic eruption with lava fountains. People were driving up and watching it. They were calling it the tourist eruption.
Yeah.
And then in mid-April, the vent location changed from the flank to the summit, which has a glacier in the summit, and it was a completely different magma type. It was more dacitic. I mean, there are silicic volcanoes in Iceland too, and oddly, Ea had at least 2 separate magma bodies, and one erupted first and the other one erupted later, and it was
The silicic one produced all the ash,
Yeah.
but I never expect that in Iceland. Yeah.
Yeah, no, there's well, even Grimsvatn, which erupted the year later, that was actually basaltic, but it produced a 25-kilometer high plume with it had ash, although it was phreatomagmatic, meaning that water was mixing
Yeah.
at the vent, and the amount of ash in that got up to high elevation was not very great. You know, they did the same sort of satellite image processing that I showed here to see how much ash was in the cloud. Of course, it's difficult if you have a wet cloud because the ash rises, it gets encased in ice, and then it doesn't have the spectral properties that you need to see ash and identify it in satellite images. But it still looks like there was a lot less ash, but for some reason it still rose to 25 kilometers and sent a lot of sulfur dioxide at high elevation too.
Mhm.
But yeah, Aska volcano in 1875 was a big silicic eruption in the central rift zone. But
Mhm.
yeah, most of them are mafic.
Yeah. Yeah,
So
good.
do
Thank you.
Cities now have laws regarding the safety of if there is a volcano attack. Do cities have regular laws that?
Most of the, well, in Washington State, I'm not sure about Oregon, but certainly in Washington State, the coordination plans are drafted between counties and other stakeholders. So the USGS has been involved in coordination plans for an eruption at, you know, obviously Mount St. Helens, Mount Rainier, Mount Baker, Glacier Peak, and those have multiple authors. It's usually not the cities, but the counties that get involved because they have emergency managers who are, you know, deal with land area. And of course, in some cases, like at Mount Rainier, the National Park Service is involved. At Mount St. Helens, the Forest Service is involved. I think up at Mount Baker, the dam operator is involved at Baker Dam. So yes, there are, of course, the farther away you get from the volcanoes, the less important it is to the emergency managers. So I'm probably, even if you go to Eastern Washington, I think most of the emergency managers in those counties don't have plans. But we're trying to change that. We've, you know, in our office, we took a 3-day trip meeting with emergency managers in Eastern Washington to talk about how they should prepare. But, you know, it's harder because for ash, it could go in any direction. So there's a lot of counties that could be affected. But if you're one county in one distant location, your chances are a lot less than if you're right next to the volcano.
Thank you.
Well, hold on a second, Charles. I'm going to do one more from Zoom and then I'll come to you. All right. Stephen asked another question. What is the weakest link in the chain right now? Measurement ability, remote sensing ability, modeling ability, communication, understanding of the physical processes?
So probably you ask 5 people with different roles that same question, you'll get 5 answers. But so I'm actually I think communication is still an issue. I know that I've heard stories about the Canary Islands had a very prolonged eruption that with lava that destroyed dozens or hundreds of houses, and there was also an ash issue, but the volcano observatory that was constantly watching the eruption and basically reporting the ash plume height, the advisories that were issued by the Toulouse VAC were using plume heights that were 12 hours old, for example. There was not the communication that was needed. And if you go from one volcanic ash advisory to another, the practices they use for how do you set up your model, what observations are you using, they're still working to improve that. So 10 years ago, they started a volcanic, a best practices group. So they were meeting every couple of years and saying, well, how do you do things and how do you do things? And is there a way that we can improve this? But, you know, technology is changing with time too. And we're finding that some tools are actually very useful, but they're not, but, you know, the VACs aren't even aware of them because they're not researchers, they're forecasters. And so somebody has to go and train them on these things. And you know, there are different VACs like the Washington VAC, which deals with 600 advisories per year because they have all these, like every time Popocatépetl, which is this volcano near Mexico City, sends out a little poof, they issue an advisory. And so there's hundreds every year, and the London VAC issues 2. And when or even probably less than that, it's 1 every few years. But everybody's scared to death when they issue 1 because it could go to Europe. So there's still a lot of differences in the way that things are done. And because the technology is changing with time, and because different satellite platforms are only available in certain parts of the world, it probably will be, I don't know if they'll ever get completely standardized, but they're obviously trying to improve.
Can you do, when he asked the question, will you just repeat it?
Yep.
Okay.
So you are in a very, very horizontal region and cover most of the Pacific and also in the Atlantic. Is the Vancouver facility the only Vancouver volcano center that in Vancouver, Washington, for that entire region?
You're referring to the VAC region, I presume, right? Yeah. So let me just go back to that map. So no, actually, so to repeat the question, Charles was asking, I think you're asking, are we the only volcano observatory in the Washington VAC region? Yeah. Well, there's, so the USGS has 5 volcano observatories, but so Yellowstone Volcano Observatory you can kind of forget about, because unless Yellowstone erupts again, it's not going to be a big deal. The California Volcano Observatory in Menlo Park, California, has several volcanic centers in California they deal with, but none of them is likely to erupt in the next 50 years. Of course, the Cascades Volcano Observatory, we haven't had an eruption since 2004 or 2008, but we could get one, you know, again in our lifetimes. And then the Hawaiian Volcano Observatory is, you know, they're usually dealing with something, but not really anything to do with ash. But, you know, there's volcano observatories throughout all the Central American countries and Colombia and Ecuador. So they and also the Caribbean. So they deal, and those are actually where most of the activity is in the Washington back region.
You said that the Mount St. Helens eruption was 9 hours, and so it started about 8 o'clock in the morning, didn't it? Ended about 4 in the afternoon.
Yeah, 8:30. I mean, it petered out over a period of a couple hours, but to 5, like working hours basically.
Taken about 1 or 1:30 in the afternoon. Was that at the peak of the eruption?
So the highest plume was near the end, around 4 or 5 p.m. But there was a change in the character of the eruption around noon. So at 8:30, we had the landslide and the lateral blast, which sent everything north. And then, so this big pyroclastic flow went north, and then just the heat of that rose, this giant cloud rose up to 32 kilometers and formed this big umbrella cloud. That was the highest plume of the entire day. And it was just rising off of that pyroclastic flow. And then really nothing was going on at the vent until sometime after 9 a.m. And then a plume started developing, and it was 10 or 12 kilometers high throughout the morning. And around noon, we started seeing pyroclastic flows coming off of that. It was still Plinian column, a buoyant column, but these pyroclastic flows were peeling off and going down the north flank of the volcano into the pumice plain area. And then there were additional plumes rising from those that were feeding into the cloud. And so that went on much of the afternoon, both the pyroclastic flow activity and the buoyant Plinian column rising from the vent area. But we actually had plume heights because somebody in the National Weather Service was recording them on radar every hour or so. And you could see this time series of, you know, this giant plume at 8:30, and then 12, 14, 15, 16, 17 until 5 p.m. And then it rapidly drops off.
Thanks, Larry, for
Yeah.
joining us this
It
evening.
was a pleasure.
Sure appreciate it. Sorry.
Adjourn for the Zoom.
Adjourn for the Zoom. Okay.
Yes, you're welcome.
Well, now you don't have such a your commute. Yeah, I assume you live in Vancouver? Or?
Yeah, it's going to be an easier drive back home than it was.
Yeah, sometimes it's nasty. Well, we sure enjoyed this.
Well, I always enjoy giving this talk.
Yeah, if you're able to come down to it's called the Columbia Aviation Association. It's in Aurora.
Okay.
Yeah, you wouldn't have to change a thing. And like you said, there'd be some pilots that would have some.
Yeah, I would love to hear stories from them if they have any stories from that time period.
It's really hard to explain you know, the first time I flew, and I could see, I mean, it's visual, well, you know what visual flight rules,
Yeah.
conditions, but I'll tell you what, you still realize that you have like a paper carburetor filter for your plane.
Yeah.
What's this doing to that?
Yeah.
You know, you still
Yeah.
because you could see it. It's clear out. The sun's out, but you can see the particles in the air.
Yeah, no, I haven't really heard any stories about people who've flown into ash clouds with, just a propeller plane. I'm sure they're out there, but the real harrowing ones, of course, are the jets that fly into
Oh,
ash.
hey, by the way, you know, as you were talking, there were a couple of other kind of personal experiences. So my house got crushed by 10 to 2 buttons because I lived in the Philippines.
Really?
Yeah,
Oh my gosh.
yeah, right there. So I mean, I wasn't there, but I left for a couple of years, and I was stationed at Clark Field for 2 years. And what else was? Anyway, something else. Oh, I was in C-130s at McCord Field.
Wow.
C-130. I
Oh my
have
gosh.
3,200 flying hours.
Oh, jeez.
Yeah, it's pretty funny.
Yeah. Yeah, I would love to. One of the guys in our office was an expert witness in the trial that came out of that, because
Oh, yeah.
apparently Transamerica owned the engines. I don't know how that works, like,
I don't,
but
I've never heard of that, but yeah, they're Allison engines. It's a turboprop engine. So it's basically, the props go around, but it's really a jet engine.
yeah, right,
Yeah.
right. And so I guess they were the ones suing the pilot or something. But one of the guys in our office was an expert witness, and 5 years or so ago, he said he still remembered the name of the judge who was on the case, and he called him, and it turned out the guy still had the transcripts from that court case in his basement. So I got the transcripts from the voice communication. So it's pretty clear that the pilot was making his own decisions about. I think he wanted to fly into a plume.
Yeah. Oh, yeah. Yeah, I met a lot of cowboys.
Yeah.
Yeah. In
Yeah.
that business. Yeah, but that's what he did.
Yep.
He says he didn't, but he did.
Yeah, exactly.